Picture standing at the edge of a vast cosmic ocean, where the fabric of reality isn't rigid or fixed but fluid, dynamic, almost alive. What if I told you that time isn't a steady, unchanging force but something that can stretch, warp, and even fold? This isn't science fiction, it's the mind-bending reality of spacetime, the invisible framework that shapes everything from the motion of planets to the ticking of your watch. Today, we're embarking on a journey through 38 revolutionary models that peel back the layers of this cosmic mystery, revealing how the universe works at its deepest level. Think about the last time you used GPS to navigate somewhere. That simple convenience relies on Einstein's theory of relativity, proof that spacetime isn't just abstract physics, but something woven into our daily lives. From black holes bending light like a funhouse mirror to quantum particles defying our notions of cause and effect, the spacetime continuum is full of surprises that challenge how we perceive reality. And here's the thrilling part. Scientists are still uncovering its secrets, each discovery reshaping our understanding of existence itself. So why does this matter to you? Because spacetime isn't just a curiosity for physicists in lab coats, it's the stage on which the entire universe performs. Whether it's the way your phone pinpoints your location or the mind-blowing possibility of wormholes connecting distant corners of the cosmos, these ideas touch our lives in ways we rarely stop to consider. Over the next few minutes, we'll unravel these concepts together, using stunning visual metaphors, real-world examples, and breakthroughs that bridge the gap between theory and tangible wonder. Ready to see the universe in a whole new light? Let's dive in. Imagine dropping a bowling ball onto a trampoline, the way it stretches the fabric downward, creating a deep dip. Now replace the trampoline with spacetime itself, and you've got the rubber sheet analogy, one of the most intuitive ways to grasp how gravity really works. In this model, stars and planets aren't just objects floating in empty space. They're like weights pressing into the very fabric of the universe, warping it so that other objects move along curved paths. Think of Earth orbiting the Sun. It's not being pulled by some invisible force, but simply following the natural curve created by the Sun's immense mass. This idea didn't just come out of thin air. Einstein's field equations, a set of mind-bending mathematical expressions, describe exactly how matter and energy distort spacetime. The equations reveal that gravity isn't a force in the traditional sense, but rather the result of geometry, like walking in a straight line on a globe only to end up going in circles. Yet for all its elegance, the rubber sheet model has its limits. It works beautifully in 2 dimensions, but spacetime is 4-dimensional, blending space and time into a single, flexible continuum. Some physicists argue this simplification misses the full picture, especially when dealing with extreme scenarios like black holes or the Big Bang. But here's where it gets even more fascinating. This curvature doesn't just affect planets, it bends light itself. When starlight passes near a massive object like a galaxy, its path curves, a phenomenon called gravitational lensing. It's as if spacetime acts like a giant magnifying glass, distorting and even multiplying the images of distant stars. This isn't just theoretical. Astronomers use it to map dark matter, proving that Einstein's vision of spacetime isn't just a metaphor. It's the invisible scaffolding shaping everything we see. Gravitational lensing is like the universe's way of playing tricks on our eyes, except these illusions reveal profound truths about reality itself. Picture light from a distant star traveling across the cosmos for billions of years, only to have its path twisted by the gravitational pull of a massive galaxy in its way. The result, a cosmic mirage where a single star might appear as multiple smeared arcs or even a perfect ring around the intervening galaxy. This isn't just theoretical. The Hubble Space Telescope has captured countless examples of these warped galactic portraits, earning them the nickname Einstein rings. The story of how we confirmed this phenomenon reads like a blockbuster scientific drama. In 1919, during a total solar eclipse, astronomers observed starlight bending around the sun exactly as Einstein's equations predicted. The discovery made headlines worldwide, transforming relativity from an abstract idea into a cornerstone of modern physics. Fast forward to today, and gravitational lensing has become one of astronomy's most powerful tools. By analyzing how light distorts around galaxy clusters, scientists can map the invisible scaffolding of dark matter, uncovering the hidden structure of the universe. But the implications go even deeper. Some researchers speculate that subtle anomalies in lensing patterns could hint at extra dimensions, a tantalizing clue for string theory, which proposes that spacetime isn't just four-dimensional, but may have as many as 10 or 11 dimensions curled up in ways too tiny to see directly. Imagine spacetime as a vast, rippling ocean where these hidden dimensions create barely detectable eddies in the fabric of gravity. While we haven't found definitive proof yet, the search pushes the boundaries of what lensing can reveal. And then there's the ultimate cosmic shortcut, wormholes. If spacetime can bend, could it also fold, creating tunnels connecting distant points in an instant? The math suggests it's possible, but the energy required would dwarf anything we know how to harness. Yet the idea captivates physicists and sci-fi fans alike, because if wormholes exist, they'd rewrite the rules of travel, time, and even causality itself. From bending light to bending the very fabric of reality, these models show how spacetime isn't just a backdrop for the universe, but an active, dynamic player in its grandest mysteries. What if you could take a cosmic shortcut, folding the universe like a piece of paper and stepping through the crease? That's the tantalizing promise of wormholes, theoretical tunnels through spacetime that could connect distant points in an instant, or even bridge entirely different universes. While they've been a sci-fi staple for decades, these cosmic passageways aren't just fantasy. The math actually allows for their existence, thanks to solutions like the Einstein-Rosen bridge, a concept born from Einstein's own equations. Picture two black holes linked by a throat of warped spacetime, a tunnel where matter and light could, in theory, traverse unimaginable distances. But here's the catch: wormholes, as we understand them, would be incredibly unstable. Without some form of exotic matter, a substance with negative energy that defies gravity's usual pull, these tunnels would collapse faster than they could form. It's like trying to hold open a doorway made of smoke. The moment you let go, it vanishes. Even if we could stabilize them, Stephen Hawking's chronology protection conjecture suggests time travel paradoxes might tear them apart. Imagine going back in time and accidentally preventing your own birth, a logical inconsistency so disruptive that the universe might simply refuse to allow it. Yet the story doesn't end there. NASA ER EPR proposal weaves wormholes into the fabric of quantum physics, suggesting a bizarre connection between these cosmic shortcuts and quantum entanglement. When two particles become entangled, their states mirror each other instantly, no matter how far apart they are. It's as if they're linked by a microscopic wormhole, a hidden thread stitching the universe together at its smallest scales. Some theorists take this even further, proposing that wormholes could be evidence of a holographic universe where our three-dimensional reality is just a projection of information encoded on a distant, two-dimensional surface. And then there's the multiverse angle. If wormholes do exist, could they lead not just to other places in our universe, but to entirely separate realities? The idea might sound like something from a comic book, but it's grounded in serious physics. Certain interpretations of quantum mechanics suggest parallel universes constantly branch off from our own, each with its own version of history. Wormholes might be the bridges between these worlds, though passing through one would likely require energies beyond anything we can fathom today. Whether they're cosmic shortcuts, time machines, or gateways to the multiverse, wormholes remind us that spacetime is far stranger and far more malleable than our everyday experience suggests. If time feels like a river sweeping us forward, the block universe model flips that intuition on its head, suggesting past, present, and future all exist simultaneously, like frames in an infinite cosmic film reel. This radical idea, first formalized by Hermann Minkowski in the early 20th century, treats spacetime as an unchanging four-dimensional structure where every event from the birth of stars to your next breath is permanently etched into reality. Think of it as a vast library where every moment exists forever on its own shelf, and what we call now is just the page we happen to be reading. Minkowski's spacetime diagrams bring this concept to life with elegant simplicity. Picture a grid where horizontal lines represent space and vertical lines track time. Every star explosion, every handshake, every whispered word becomes a fixed point on this map. There's no special, moving present in this view. The distinction between already happened and yet to come is just a quirk of human perception. Philosophers have wrestled with this for centuries. If the future is already out there, does free will even exist? Or are we just passengers on a predetermined ride, mistaking the illusion of choice for reality? Quantum mechanics throws another wrench into the works. Experiments like the delayed choice quantum eraser suggest particles can retroactively influence events that technically occurred before the experiment was set up, as if the universe is editing its own script after the fact. This isn't time travel in the sci-fi sense, but it does hint that causality might be more flexible than we thought. Even Einstein struggled with these implications, famously writing that for physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. So why does time feel so real to us, the arrow of time? The reason we remember the past but not the future might boil down to entropy, the universe's tendency toward disorder. Imagine a shattered glass reassembling itself. Physics allows it, but the odds are astronomically low because entropy only increases in our experience. This one-way street of disorder could be the engine behind our perception of time's flow, stitching together moments into a narrative our brains can comprehend. From cosmic scales to quantum quirks, the block universe challenges everything we think we know about time, not as a force, but as a story we tell ourselves to make sense of the infinite now. Ever watch an egg crack into a sizzling pan, its yolk spreading into a perfect golden disk, and wonder why that transformation only goes one way? The answer lies in entropy, nature's relentless push toward disorder, and the hidden force behind time's arrow. Ludwig Boltzmann, the 19th century physicist who pioneered statistical mechanics, revealed something astonishing. Time's forward march isn't just a cosmic rule, it's a numbers game. At the microscopic level, particles can move in countless configurations, but the vast majority of those arrangements are messy, disordered states. An egg unscrambling itself isn't impossible, just astronomically unlikely, like a shattered window reassembling midair. This statistical tilt toward chaos traces back to the Big Bang, which left the universe in an improbably smooth, low-entropy state, a cosmic wound-up spring slowly unwinding. Every galaxy, every cup of coffee cooling on your desk, even the heat radiating from your body, is part of this grand slide toward equilibrium. But here's where it gets wild. If our universe is just one bubble in a vast multiverse, could other regions have arrows of time pointing backward? Some cosmologists speculate that in these alternate realms, eggs might spontaneously unscramble, and smoke would funnel back into cigarettes' realities where entropy runs in reverse. Quantum physics adds another twist. Emerging theories suggest time itself might not be fundamental, but instead emerge from the churning interactions of tiny particles. Picture spacetime as a turbulent ocean, where microscopic quantum events create a froth of fleeting timelines, what physicists call quantum foam. In this view, the smooth flow of time we experience could be an illusion, a large-scale averaging of countless chaotic interactions. Experiments with entangled particles already hint at this blurring of cause and effect, where events seem to influence each other outside the usual bounds of time. So is time's arrow written into the universe's DNA, or is it more like a weather vane pointing different ways in different cosmic pockets? The answer could redefine not just physics but philosophy. If entropy isn't destiny, if time's flow is more fluid than fixed, then reality might be far stranger, far more malleable than Boltzmann ever imagined. From scrambled eggs to quantum foam, the puzzle of time's arrow reminds us that even the most familiar phenomena hold universe-shaking secrets. Zoom in far enough past atoms, past quarks, down to scales a billion times smaller than a grain of sand, and spacetime itself begins to fizz like a cosmic soda. This is quantum foam, John Wheeler's radical vision of a universe where the smooth, predictable fabric of relativity gives way to a seething, turbulent froth. At these unimaginably tiny Planck lengths, spacetime isn't a static stage but a boiling cauldron of virtual particles blinking in and out of existence, warping geometry itself into fleeting bubbles and tunnels. Picture the surface of a stormy ocean, but instead of waves, you've got microscopic black holes and wormholes forming and vanishing in trillionths of a second. A reality so unstable, so chaotic, that even concepts like before and after lose meaning. The implications are staggering. If spacetime is pixelated at this level, then the universe might operate more like a cosmic computer screen than a continuous sheet, with every event playing out on a grid of indivisible spacetime pixels. Fermilab's holometer experiment aimed to detect this granularity by firing lasers down perpendicular tunnels, searching for telltale jitter in the beams, hints that spacetime itself vibrates like static on an old TV. While results were inconclusive, the hunt continues, because if quantum foam is real, it could bridge the century-old rift between relativity and quantum mechanics. Enter loop quantum gravity, a daring framework that treats space as a woven tapestry of tiny, interconnected loops. Imagine spacetime not as a blank canvas but as a mesh of threads, where each knot represents a discrete quantum of volume. In this view, the Big Bang wasn't a singularity but a quantum bounce, a moment when a previous universe collapsed and rebounded, like a stretched spring snapping back. No infinite densities, no breakdown of physics, just a cosmic reset button. But what if spacetime isn't even the deepest layer? Holographic theory flips the script entirely, proposing that our three-dimensional reality, stars, planets, even your morning coffee, might be a projection of information encoded on a distant, two-dimensional surface. Like a movie screen creating the illusion of depth, spacetime could be a shadow cast by quantum bits we can't yet see. It's an idea so counterintuitive that even physicists grapple with its meaning. If true, the solid world around us is nothing more than a hologram, with the true source code of reality hidden at the universe's edges. From foam to fabric, from pixels to projections, these models force us to confront a humbling possibility. Spacetime, the very foundation of existence, might be emergent, a side effect of something far stranger lurking beneath. Whether it's quantum loops, holograms, or some undiscovered structure, one thing's certain: the closer we look, the less space-time behaves like anything we thought we knew. What if everything you see, your hands, the stars, even the air you breathe, is just an illusion, a three-dimensional projection from information etched onto a distant, two-dimensional surface? This is the holographic principle, a mind-bending idea that turns our understanding of reality inside out. It started with a puzzle about black holes. When matter falls into one, what happens to its information? Quantum mechanics says information can't be destroyed, but black holes seem to erase it completely. Gerard T. Hooft and Leonard Susskind proposed a revolutionary answer. The information isn't lost, it's smeared across the black hole's event horizon like cosmic ink on a spherical canvas. The math behind this is staggering. A black hole's entropy, a measure of its hidden information, doesn't scale with its volume but with its surface area. It's as if the entire interior of the black hole is somehow encoded on its outer shell. Take this idea further, and you arrive at the AD/CFT correspondence, a mathematical bridge between gravity and quantum physics. In this framework, a universe with gravity like ours can be perfectly described by a quantum field theory operating on its boundary, a lower-dimensional shadow world without gravity at all. Imagine a movie where every detail, every explosion, every whispered line of dialogue is stored not in the three-dimensional scenes but in the pixels of the flat screen projecting it. This isn't just abstract theorizing. Experiments with quark-gluon plasma, a super-hot primordial soup of particles created in particle colliders, show behavior that aligns eerily with holographic predictions. Even stranger, some versions of the principle suggest time itself might emerge from quantum entanglement, like a collective hallucination agreed upon by trillions of interacting particles. If true, the solidity of your morning coffee cup, the warmth of sunlight on your skin, all of it could be a kind of cosmic augmented reality with the true source code of existence hidden at the universe's edges. But how do we test such an outlandish idea? Black holes, those cosmic shredders of spacetime, might hold the key. When two black holes collide, the resulting gravitational waves ripple through spacetime like echoes of a distant drum. Hidden in those waves could be subtle fingerprints of holography, tiny deviations from Einstein's predictions that reveal whether spacetime is truly fundamental or just a shimmering mirage. The implications are dizzying. If the holographic principle is correct, then the universe isn't just stranger than we imagine, it's stranger than we can imagine. A cosmic sleight of hand where depth, time, and even causality are illusions woven from information we've only begun to decode. Falling into a black hole sounds like the ultimate cosmic freefall until quantum physics crashes the party with a nightmarish twist. Einstein's equations paint a serene picture: cross the event horizon, and you'd glide smoothly toward the singularity, blissfully unaware of your fate. But quantum mechanics flips this into a horror story, predicting a blazing wall of high-energy particles just inside the horizon, a so-called firewall that would vaporize you instantly. This isn't just sci-fi speculation. It's the heart of the AMPS paradox, a clash between two pillars of physics that threatens to unravel our understanding of spacetime itself. The paradox gets its teeth from a quantum phenomenon called entanglement. Imagine two particles linked so intimately that changing one instantly affects the other, no matter how far apart they are. Now picture one particle falling into a black hole while its partner remains outside. According to quantum rules, the outsider must stay entangled with its doomed twin, but black holes also radiate energy, slowly evaporating via Hawking radiation. Here's the catch: that radiation must somehow carry information about everything the black hole swallowed. meaning it too should be entangled with the original infalling particle. Quantum mechanics forbids a particle from being entangled with two things at once, so something's got to give. The firewall emerges as a brutal solution. Sever the original entanglement in a fiery burst, preserving the rules of quantum theory at the cost of turning the event horizon into a death zone. But physicists hate paradoxes, and the hunt for alternatives is on. One audacious idea, dubbed ER equals EPR, suggests that entangled particles might be connected by microscopic wormholes, Einstein-Rosen bridges threading through spacetime like invisible stitches. In this view, falling into a black hole wouldn't torch you. You'd just emerge somewhere else, woven into the fabric of the cosmos via quantum threads we can't yet see. Then there's the fuzzball proposal from string theory, which reimagines black holes not as empty pits but as tangled knots of vibrating strings, their surfaces buzzing with quantum energy. No smooth horizon, no firewall, just a dense, fuzzy boundary where spacetime itself gets rewritten at the tiniest scales. What makes this more than abstract theorizing is the stakes. If firewalls are real, Einstein's smooth spacetime shatters at black hole boundaries. If ER equals EPR holds, wormholes might be woven into the quantum code of the universe. Either way, the resolution points toward a deeper theory waiting in the wings, one where gravity and quantum mechanics finally shake hands. From lethal firewalls to cosmic threads, this battle isn't just about black holes. It's a proxy war for the soul of reality, forcing us to ask, is spacetime fundamental, or just a fragile illusion draped over quantum truths we've yet to fully grasp? Forget smooth, continuous space. What if reality is stitched together from tiny, indivisible threads, like a cosmic tapestry woven from the fabric of existence itself? That's the bold vision of loop quantum gravity, a theory that dares to rewrite spacetime not as a blank canvas but as a dynamic network of interwoven loops. Unlike string theories, vibrating filaments floating in space, these loops are space itself, knotted into a fine mesh where each intersection represents the smallest possible unit of volume, a quantum of space no bigger than a Planck length. Picture the universe as a vast, shifting web where even the emptiness between stars hums with granular structure, a reality where nothing is an illusion and every void pulses with quantum geometry. The magic lies in spin networks, intricate diagrams that map how these loops intertwine. Each thread carries a quantum of area, and where they cross, they create nodes, like microscopic crossroads where space itself is knotted into existence. These aren't static knots, they evolve dynamically, updating the cosmic blueprint with every passing moment. The result, a universe where space isn't infinitely divisible but pixelated, like a digital image zoomed in until you see the individual pixels. This granularity solves one of physics' most vexing problems, the singularity at the Big Bang. Instead of a point of infinite density, loop quantum gravity proposes a big bounce, a moment when a previous universe collapsed and rebounded like a spring, its energy compressed to the limit before snapping back outward into our expanding cosmos. But no theory is flawless. While loop quantum gravity elegantly sidesteps singularities, it struggles to explain why gravity feels like a force in our everyday lives. Why does an apple fall from a tree if gravity is just the curvature of this quantum tapestry? Proponents argue that Einstein's smooth spacetime emerges from the collective behavior of trillions of loops, like how a woven blanket feels solid despite being made of individual threads. Yet critics counter that the math hasn't yet bridged the gap between this microstructure and the gravity we observe. Where the theory shines is in its testability. Some models predict subtle imprints of the bounce in ancient light from the early universe, or unique signatures in gamma-ray bursts, cosmic fireworks that might carry echoes of spacetime's granularity. Experiments like the Fermi Gamma Ray Space Telescope are already hunting for these fingerprints, though definitive proof remains elusive. Now contrast this with string theory, its flashier rival. Where loop quantum gravity builds space from knots, string theory imagines reality as a symphony of vibrating strings, with particles as notes and forces as harmonies. One embraces granularity, the other elegance in higher dimensions. Both grapple with the same cosmic questions, but their languages couldn't be more different. One a quantum quilt, the other a multidimensional concerto. Yet their shared goal unites them, to reveal whether spacetime is fundamental or merely the shadow of something deeper. What if every particle in the universe, every electron, every photon, isn't a tiny dot but a vibrating string, humming different notes to create the symphony of reality? This is the heart of string theory, where the building blocks of nature aren't points but impossibly small loops, each oscillation producing a different particle's properties. But there's a catch. These strings don't dance in the 3 dimensions we know. They require 10 or even 11 dimensions to make the math work, leaving us with a puzzle. Where are these extra dimensions hiding, and why don't we notice them? The answer lies in Calabi-Yau manifolds, intricate geometric shapes so tightly curled that they're effectively invisible at everyday scales. Imagine a garden hose. From a distance, it looks like a one-dimensional line, but up close, you see it's a tube with a circular cross-section. Extra dimensions could be similarly compactified, folded into complex patterns at scales a billion times smaller than an atom. Yet their geometry isn't just academic, it determines the laws of physics in our visible universe. The way these shapes vibrate and twist could explain why we have exactly 4 fundamental forces, why particles have their specific masses, even why the universe has more matter than antimatter. String theory's grandest ambition is M-theory, a framework that stitches together 5 competing string theories by adding an 11th dimension and introducing membranes, or branes, higher dimensional objects that could be entire universes floating in a vast multiverse. Picture our cosmos as a slice of bread in a cosmic loaf, with other universes just millimeters away in a dimension we can't perceive. Collisions between these branes might even trigger big bangs, suggesting our universe's birth wasn't unique, just one event in an endless cycle of creation. But for all its elegance, string theory faces a glaring challenge: 0 experimental proof. No instrument has ever detected a string or an extra dimension. Some critics argue it's more philosophy than physics, a beautiful mathematical castle floating untethered from reality. Yet hope isn't lost. If extra dimensions exist, particle colliders like the Large Hadron Collider might someday produce microscopic black holes fleeting, evaporating pinpricks that could only form if gravity leaks into hidden dimensions. Other experiments hunt for subtle deviations in gravity at submillimeter scales, where extra dimensions might subtly alter the inverse square law. The stakes couldn't be higher. If string theory is right, it wouldn't just unify gravity and quantum mechanics, it would reveal that every law of physics, every constant we hold as fixed, is just a local byproduct of how our particular Calabi-Yau manifold happens to vibrate. We might live in a cosmic accident, one tuning of the strings among infinite possibilities. From vibrating threads to hidden geometries, this model doesn't just tweak our understanding of spacetime, it rewrites the entire score of reality. Imagine building the universe from scratch, not with equations or strings, but with cosmic Legos, tiny, triangular blocks of spacetime snapped together in endless configurations. This is the essence of causal dynamical triangulations, a radical approach that ditches smooth geometry for a digital playground where reality emerges from countless simple shapes. Picture slicing spacetime into microscopic tetrahedrons, each a building block obeying 2 golden rules: causality, no time travel loops allowed, and a fixed speed for light. Then let supercomputers shuffle these pieces at random, evolving them step by step to see what large-scale structure crystallizes from the chaos. The results are astonishing. Without any top-down design, this bottom-up simulation consistently generates a four-dimensional universe remarkably like ours: 3 dimensions of space and 1 of time. It's as if you dropped a box of jigsaw pieces and watched them spontaneously assemble into a flawless map of the world. This alignment with observed reality is no small feat, especially since the model starts with no preconceptions about dimensionality. Unlike string theory's 10 or 11 dimensions or brain-world scenarios, here the familiar 4 arise naturally from the quantum fray, suggesting our perception of space-time might be an emergent property rather than a fundamental truth. Where this model truly shines is in its computational elegance. By treating space-time as a network of discrete triangles, each interaction governed by simple rules, it sidesteps the infinite complexities that plague continuum-based theories. There's no need for exotic matter or undiscovered particles, just geometry and probability doing their dance. Yet it shares surprising common ground with loop quantum gravity's woven space-time, hinting that discreteness might be a universal feature of quantum gravity. But don't mistake simplicity for limitation. These simulations have uncovered a phase transition in spacetime itself, a critical threshold where the jumble of triangles suddenly clicks into an orderly 4-dimensional lattice. Below this threshold, spacetime remains a chaotic foam. Above it, the universe as we know it takes shape. Some theorists speculate this could mirror the Big Bang's aftermath, when the primordial cosmos cooled into recognizable structure. The implications ripple outward. If spacetime is truly assembled from these quantum pixels, then black holes might be knots where the triangulation frays, and the arrow of time could emerge from causality's unbroken chain. Even dark energy finds a potential explanation, not as a mysterious force, but as a side effect of how spacetime triangles fill in the cosmic gaps. While still in its infancy, causal dynamical triangulations offer something rare, a testable pathway to quantum gravity, where supercomputers act as telescopes probing spacetime's atomic architecture. In a field often divided by abstract math, this model reminds us that sometimes the universe's deepest secrets hide in the simplest shapes. What if the laws of physics aren't laws at all, but cosmic habits, rules that evolved over countless generations of universes, fine-tuned not by chance, but by a form of natural selection? This is the provocative heart of Lee Smollen's cosmological natural selection, a theory that grafts Darwinian principles onto the fabric of spacetime itself. Imagine black holes as cosmic seeds, each collapse spawning a new universe with slightly tweaked physical constants like genetic mutations in an endless lineage of reality. In this view, our universe isn't just one random roll of the dice in a multiverse casino. It's the product of a grand evolutionary process where universes compete to maximize black hole production. The elegance lies in its testability. If Smollen's right, universes optimized for black holes should share certain traits, like neutron stars hovering just below the mass threshold needed to collapse. These dense stellar corpses could be fossils of cosmic selection, their properties revealing whether gravity, the nuclear forces, and other constants are truly fixed or merely local quirks of our universe's lineage. It's a radical departure from traditional fine-tuning arguments, which often invoke an infinite multiverse to explain why our cosmos seems improbably suited for life. Instead of shrugging at coincidence, Smollen offers a mechanism. Universes that produce more black holes reproduce more, passing on their traits like cosmic DNA. Critics pounce on the theory's unproven leaps, like how baby universes might inherit physical constants, or whether black hole singularities could truly birth new realities. Yet the idea resonates because it replaces metaphysical hand-waving with something resembling scientific causality. Even Stephen Hawking found it compelling enough to entertain in his final work, pondering whether spacetime's rules might emerge from deeper evolutionary principles. Now contrast this with the Anthropic Principle, which argues that we observe a life-friendly universe because, well, we're here to observe it. In a multiverse of infinite variations, some pockets will inevitably hit the jackpot of conditions for complexity. But Smolin's model offers a twist. What if fine-tuning isn't just dumb luck, but the result of a cosmic bias toward black hole-rich environments? After all, the same stars that forge carbon in their cores also collapse into black holes, linking life's prerequisites with the universe's reproductive success. The implications ripple beyond astrophysics. If constants evolve, then the quest for a theory of everything might need to account not just for how the universe works, but how it learned to work. From black hole nurseries to neutron star signatures, this Darwinian lens turns spacetime into something alive, dynamic, a participant in its own unfolding story rather than a static stage. Whether it's testable or just a beautiful metaphor, one thing's certain: the idea that universes grow, change, and even reproduce challenges us to see reality not as a fixed edifice, but as a chapter in an epic we've only begun to read. Imagine a universe where gravity was slightly stronger. Stars would burn out in a cosmic blink. If electromagnetism were weaker, atoms couldn't bond, and molecules would never form. The fact that we exist hinges on a razor-thin balance of numbers, fundamental constants so precisely tuned that altering any by a fraction would render life impossible. This is the fine-tuning problem, one of spacetime's most haunting mysteries. Why does our universe seem custom-built for complexity when the vast majority of possible settings would lead to a sterile void? One compelling answer comes from the Anthropic Principle. We observe a life-friendly universe simply because we're here to observe it. In a multiverse where countless universes bubble into existence with random constants, some will inevitably hit the jackpot. It's like buying every possible lottery ticket. Eventually, one wins. String theory's landscape of possible Calabi-Yau manifolds lends mathematical weight to this idea, suggesting our universe might be one of countless variations in an unfathomably vast cosmic ensemble. But critics argue this explanation feels like a cop-out, replacing one mystery with an even bigger one. If we can't detect other universes, does invoking them really solve anything? Enter Brand's Dick Gravity, a twist on Einstein's relativity where the gravitational constant isn't fixed but evolves over time. Think of it as cosmic climate change, gravity's strength shifting subtly as the universe ages. This could mean constants aren't arbitrary but dynamic, adjusting to some deeper equilibrium we haven't uncovered yet. Some versions even allow for regional variations, like cosmic continents with slightly different physics. Yet experiments tightly constrain how much these constants can wiggle, leaving little room for dramatic changes. Then there's the mind-bending notion of a self-sampling universe, a cosmos where consciousness itself plays a role in shaping reality. In this view, the universe fine-tunes itself because observers are necessary to collapse quantum probabilities into definite outcomes. It's as if spacetime is a grand experiment that only becomes real when measured, with life emerging as both product and participant. While this smacks of philosophy, quantum mechanics observer effect gives it a faint scientific veneer. Could the universe be tuning itself for the very act of observation? Roger Penrose's conformal cyclic cosmology offers a different escape hatch. If our universe is just one cycle in an infinite series, each beginning with a big bang and ending in a heat death, then the constants might not be fine-tuned at all, just inevitable over enough iterations. Like a deck of cards shuffled endlessly, every possible configuration eventually appears. Here, fine-tuning isn't a miracle but a statistical certainty given infinite time. Whether through multiverses, mutable constants, or cosmic cycles, these models all grapple with the same awe-inspiring truth. The universe's ability to host life feels less like accident and more like a puzzle waiting to be solved. What if the end of our universe isn't an ending at all, but the seed of a new cosmic dawn, a cycle where the ashes of one reality birth the fire of the next? Roger Penrose's conformal cyclic cosmology dares to propose just that, an infinite loop of universes, each stretching from Big Bang to heat death, only to reset in a breathtaking cosmic encore. Here's how it works. As our universe expands toward maximum entropy, all matter eventually decays into radiation, and black holes evaporate into photons. At this distant point, spacetime becomes so vast and uniform that it loses any sense of scale, a state mathematically identical to the smooth, energy-rich conditions of a new Big Bang. The universe forgets its own size, and infinity folds back to zero. Penrose's genius lies in the geometry. By treating the far future and distant past as conformally equivalent, meaning they share the same underlying shape despite different scales, he sidesteps the need for a singularity. There's no mysterious starting point, just an endless Ouroboros of spacetime. The most tantalizing evidence, strange, concentric rings in the cosmic microwave background, dubbed Hawking points, which Penrose argues are imprints of supermassive black holes from a previous cosmic cycle. These faint ripples, he claims, are the last whispers of ancient collisions, echoing across eons like cosmic fingerprints. Yet the model isn't without controversy. The biggest hurdle is entropy. How does a universe in thermodynamic equilibrium, a featureless sea of radiation, suddenly reset to the low entropy order of a new Big Bang? Penrose suggests gravitational waves could carry away entropy, effectively scrubbing the cosmic slate clean. Skeptics counter that this stretches known physics, but if true, it would rewrite our understanding of time itself. No longer a one-way street, but a Möbius strip where beginnings and endings blur. Now contrast this with quantum entanglement, where particles defy spacetime's usual rules. If two entangled photons can instantaneously mirror each other across light years, what does that mean for locality? The idea that objects need time to influence one another. Some theorists propose entanglement might be the stitches holding Penrose's cosmic cycles together, with quantum links persisting even across universal resets. Imagine the fabric of reality not as a series of disconnected chapters, but as a single, entangled tapestry woven across infinite iterations. From black hole echoes to quantum threads, these ideas don't just challenge our notions of spacetime, they dissolve the line between past, present, and future entirely. Einstein famously dismissed it as spooky action at a distance, the baffling phenomenon where two particles, no matter how far apart, remain mysteriously linked, their fates intertwined faster than light could travel between them. Quantum entanglement isn't just a theoretical curiosity, it's a fundamental feature of reality that's been confirmed in labs worldwide. Picture tossing a pair of dice in Tokyo and New York, only to find they always land matching numbers instantly and inexplicably. This isn't magic, it's the universe operating at its most basic level, where particles communicate in ways that defy classical notions of space and time. The implications are staggering. If entangled particles can coordinate instantly across cosmic distances, then locality, the idea that objects need time to influence one another, crumbles. This shakes the very foundations of spacetime, suggesting it might not be the immutable stage we once thought, but something far more fluid. Enter the holographic principle and the ER equals EPR conjecture, which propose a radical solution. Entanglement doesn't happen through spacetime, it might actually create spacetime. Think of it like a cosmic internet where quantum links between particles weave the fabric of reality itself, stitching together the geometry we perceive as distance and dimension. Experiments with entangled photons have already shown correlations that can't be explained by hidden variables or classical physics. In 2015, the Delft loophole-free Bell test sealed the deal, proving entanglement's defiance of local realism. But the real shocker came when theorists realized black holes might be entangled with the radiation they emit, implying that spacetime itself could emerge from a vast, underlying quantum network. It's as if the universe runs on a quantum version of social media, where every particle's status update instantly affects its entangled partners, building the illusion of a continuous, three-dimensional world. This perspective flips causality on its head. Instead of spacetime enabling interactions, interactions might construct spacetime. Imagine building a house not with bricks, but by defining the relationships between its rooms. The structure emerges from the connections. If true, then the next model, quantum gravity, takes this idea even further, proposing that spacetime is literally a graph, a web of quantum nodes where distance is just a measure of how entangled 2 points are. The universe, in this view, isn't smooth or continuous, but a dynamic network constantly rewriting its own rules, with entanglement as the invisible hand sculpting reality. From spooky action to cosmic architecture, these ideas don't just challenge Einstein's objections. They invite us to see spacetime not as a given, but as a grand illusion, a hologram painted by quantum threads we're only beginning to untangle. Take the vast cosmic web of galaxies with its sprawling filaments and voids, and shrink it down a trillion times. What you'd find isn't smooth spacetime, but a buzzing digital network of quantum nodes, each connected by invisible threads. This is quantum gravity, a model where the universe at its most fundamental level resembles a vast, ever-changing social network, with space itself emerging from the strength of connections between points. Picture the early universe not as a seething plasma, but as a frenetic game of quantum connect the dots, where particles weren't moving through space, they were defining it with every interaction. In this radical framework, spacetime isn't born with geometry, it acquires it. At ultra-high energies, moments after the Big Bang, the universe was a featureless graph where every node could connect equally to every other. But as temperatures dropped, these connections froze unevenly, like water crystallizing into ice, locking some links while others faded. The result? Our familiar four-dimensional reality, where three spatial dimensions and time emerge as the dominant patterns in this cosmic mesh. Think of it like a crowded plaza where everyone starts as strangers, but over time, clusters form friends, families, communities, creating structure from chaos. The smoking gun for this model, cosmic strings one-dimensional defects in spacetime's quantum fabric, like cracks in frozen ice. These aren't the cosmic strings of older theories, but infinitely thin, ultra-dense threads left over from the universe's graph-like phase. If they exist, their vibrations would ripple spacetime itself, emitting gravitational waves with a unique frequency signature. Some theorists believe these waves might already be hiding in data from pulsar timing arrays, neutron stars whose ultra-precise flashes of light could reveal spacetime's subtle tremors. But the real test lies in the cosmic microwave background, the afterglow of the Big Bang. Quantum gravity predicts that cosmic strings would leave telltale kinks and step-like patterns in this ancient light, imprints of spacetime's pixelated origins. Upcoming telescopes like the Simons Observatory and Lightbird are hunting for these anomalies, which, if found, could rewrite our understanding of reality's architecture. What makes quantum gravity so compelling is its sheer audacity. It suggests that spacetime isn't a canvas but a consequence, a side effect of deeper quantum relationships. From black holes to galaxy clusters, everything we see might just be shadows cast by an invisible web of connections, a universe where geometry isn't fundamental, but the result of an epic game of quantum telephone played over 14 billion years. Whether the evidence arrives in gravity waves or ancient photons, one thing's certain: if spacetime is indeed a graph, we're only just beginning to trace its outlines. If spacetime were a novel, most models treat it like pages in a book, smooth, continuous sheets where events unfold. But causal sets imagine it more like a Twitter feed, a stream of discrete, individual moments linked by the unshakable rule that replies must come after the original tweet. In this 17th model, reality isn't a fluid continuum but a vast, shimmering chain of events, each connected by the ironclad bonds of cause and effect. No smooth geometry, no warping fabric, just a cosmic ledger where what happens now can only influence what happens next. The elegance lies in its simplicity. By ditching the idea of spacetime as a pre-existing stage, causal sets build reality from the ground up using just two ingredients: discrete atoms of spacetime and a partial order defining which events precede others. Picture a billion dominoes falling in perfect sequence, except here, the dominoes are the sequence, with no need for a table beneath them. This minimalist approach sidesteps the infinities that plague other theories, offering a clean solution to quantum gravity's toughest puzzles. But don't mistake simplicity for weakness. Causal sets make bold predictions, like tiny, quantum fluctuations in the speed of light. These flickers would be too small to notice in everyday life, but gamma-ray bursts, cosmic explosions firing photons across billions of years, might carry faint imprints of this spacetime graininess in their arrival times. What sets this model apart is its ruthless adherence to causality. While other granular theories struggle to explain why you can't shake your grandfather's hand before he's born, causal sets bake cause and effect into their foundation. Events aren't just sprinkled randomly, they're meticulously ordered, like frames in a film reel that can't be shuffled without breaking the story. Some theorists argue this makes causal sets uniquely equipped to handle black holes, where traditional spacetime models break down. Inside the event horizon, the usual notions of before and after crumble, but in a causal set, the chain remains unbroken, offering a lifeline through the chaos. Now meet its conceptual cousin, shape dynamics. If causal sets are the universe's chronological to-do list, shape dynamics reimagines spacetime as a cosmic sculpture, where only the angles and ratios between objects hold meaning. Forget absolute distances or durations. This model suggests reality cares only about shapes and their relational geometry. It's like describing a family portrait not by measuring each person's height, but by noting who's taller than whom. Surprisingly, this perspective reproduces Einstein's general relativity without requiring spacetime to be fundamental, hinting that our obsession with continuity might be a historical accident. Together, these models whisper a provocative idea. Perhaps spacetime isn't the root of reality, but a shadow cast by deeper, more austere principles. Whether through causal chains or pure geometry, the universe might be simpler and stranger than we ever dreamed. Imagine a universe where time isn't a fundamental force, just an illusion emerging from the way shapes interact, like shadows cast by a flickering flame. This is the bold vision of shape dynamics, a model that strips spacetime down to its bare essentials, leaving only the changing geometry of three-dimensional space itself. Forget curving four-dimensional fabrics or warped timelines. Here, reality is a sequence of spatial snapshots, each morphing into the next according to pure relational rules. It's as if the cosmos is a grand flipbook where the frames aren't pictures but entire configurations of matter and energy, and time is just the turning of the pages. At first glance, this might sound like a radical departure from Einstein's relativity, but here's the twist. Shape dynamics reproduces all of general relativity's predictions with startling precision. The key lies in trading spacetime's fixed structure for evolving shapes governed by symmetry principles. Picture a cosmic game of Tetris, where the blocks are galaxies and stars, and the rules ensure their arrangements always satisfy Einstein's equations, not because spacetime bends, but because the shapes themselves evolve in perfect harmony. This isn't just mathematical sleight of hand. It's a profound shift in perspective that reframes gravity as a consequence of geometry's dance rather than a force acting on geometry. Where shape dynamics truly shines is in its handling of time. Unlike other models that struggle to reconcile time's flow with quantum mechanics' frozen probabilities, here time isn't a background stage but a derived property, a kind of cosmic clock ticking in sync with the universe's changing form. Think of it like a movie's runtime. The film exists all at once, but the experience of time emerges from how scenes transition. This elegantly sidesteps quantum mechanics' infamous problem of time, where the Schrödinger equation seems to freeze reality into a single static moment. In shape dynamics, quantum probabilities can evolve naturally because the universe's shape is always in motion, weaving time from pure relation. Yet critics highlight the model's mathematical complexity. Its equations are notoriously abstract, requiring tools from high-energy physics and differential geometry. Some argue this undermines its promise as a simpler alternative to spacetime-based theories. But proponents counter that complexity isn't a flaw if it reveals deeper truths. After all, Einstein's field equations were once deemed impenetrable, yet now underpin everything from GPS to black hole astronomy. The real test may come from quantum gravity. Shape dynamics suggests that at Planck scales, spacetime's smoothness gives way to a froth of fluctuating shapes, a quantum version of its relational ballet. If correct, this could provide a fresh path toward unifying gravity and quantum mechanics, one where entanglement and geometry arise from the same primal rules. From cosmic snapshots to quantum whispers, this model doesn't just reimagine spacetime, it challenges us to see reality as a tapestry of pure connection, where time and space are merely echoes of a deeper, shape-shifting truth. Quantum mechanics and general relativity don't just disagree about gravity, they wage an all-out war over the nature of time itself. In quantum mechanics, time is a passive backdrop, an unchanging metronome ticking steadily outside the system. Schrödinger's equation treats it like a blank canvas on which quantum states paint their probabilities. But in Einstein's universe, time is dynamic, malleable, warped by gravity, stretched by motion, woven inseparably into spacetime's fabric. This clash isn't just academic, it's a fundamental rift at the heart of physics, forcing us to ask, is time a stage or a player? One radical proposal, timeless quantum mechanics, suggests the problem isn't with time, it's with our insistence that time exists at all. Imagine freezing the universe like a paused movie frame. Every event, every particle's position, is just a static configuration. What we perceive as time's flow could be an illusion, a trick of perspective as we move through these frozen moments. In this view, quantum states don't evolve in time, they simply are, with all possible configurations coexisting eternally. It's like flipping through a deck of cards. The order isn't in the cards themselves, but in how you deal them. Yet this feels deeply at odds with our lived experience. Enter the internal clock's hypothesis, where time isn't universal but local, a property emerging from interactions within quantum systems themselves. Picture a universe with no master clock, where each particle carries its own tiny hourglass, its rhythm dictated by entanglement with nearby particles. Overlapping these rhythms could create the illusion of a unified flow, much like individual musicians in an orchestra blending into a single symphony. Experiments with quantum clocks atoms whose vibrations mark time show these devices can become entangled, their ticks syncing up in ways that hint at time's relational nature. Then there's the thermal time hypothesis, which ties time's arrow directly to thermodynamics. Instead of treating time as fundamental, it suggests time emerges from the statistical dance of particles, specifically from the correlations between quantum states as they evolve toward equilibrium. Think of a cup of coffee cooling in a room. The heat flow defines a directionality that we interpret as time. At the quantum level, this could mean that what we call time is just the universe's memory of which states are correlated with which others. It's a breathtaking inversion. Time isn't a river carrying us forward. It's the wake left by quantum systems as they forget their past configurations. This loops us back to entropy, the very concept that gave us the arrow of time in the first place. If thermal time is correct, then the reason we remember the past but not the future isn't because time flows. It's because the past is statistically more determined, a frozen record of high probability correlations. The future, by contrast, remains a haze of quantum possibility. From timeless quantum states to entangled clocks and thermodynamic correlations, these models don't just reconcile time's dual nature, they dissolve it entirely, revealing a reality where time might be the most convincing illusion of all. What if time isn't something the universe provides, but something we create, a side effect of matter and energy shuffling toward disorder? This is the provocative core of the thermal time hypothesis, where time's flow isn't a fundamental feature of reality but a statistical mirage, an illusion born from entropy's relentless climb. Carlo Rovelli, one of the architects of loop quantum gravity, takes this even further. What we call time might just be the universe's way of forgetting. Imagine a deck of cards, shuffle it, and the ordered sequence dissolves into randomness. That irreversible slide toward chaos, Rovelli argues, is what clocks actually measure, not some cosmic metronome ticking in the background. This turns everyday intuition on its head. We think of time as a river sweeping us forward, but in this view, it's more like the wake left by particles as they lose track of their past states. A clock's ticks aren't marking the passage of an independent dimension. They're counting correlations between quantum systems as they evolve toward equilibrium. Picture 2 cups of coffee, one hot, one cold, left in a room. As heat flows, their temperatures equalize and the system forgets its initial state. That process of forgetting creates what we perceive as time's arrow. It's a staggering idea. Without entropy, there'd be no time, just a static cosmos frozen in an eternal now. But if time emerges from statistics, why does it feel so vivid to us? Neuroscience offers a clue. Our brains don't passively record time, they construct it, weaving together sensory inputs into a coherent narrative. Studies of patients with time perception disorders reveal that our sense of chronology is fragile, easily disrupted by changes in memory or attention. In a way, the brain mirrors Rovelli's hypothesis. Just as thermal time arises from systems losing information, our subjective experience of time might stem from the brain's constant effort to organize and discard sensory data. The implications ripple outward. If time is emergent, not fundamental, then black holes where entropy reaches staggering extremes might warp our perception of duration in ways we've yet to grasp. Even quantum gravity's toughest puzzles, like the problem of frozen time in the Wheeler-DeWitt equation, could find resolution in this statistical dance. From the thermodynamics of coffee cups to the firing of neurons, the thermal time hypothesis doesn't just redefine clocks, it reshapes our understanding of reality itself, suggesting that the flow of time isn't woven into the cosmos but whispered into existence by countless tiny forgettings. Your brain is the ultimate time machine, not because it can travel through the ages, but because it constructs time itself, stitching together moments like frames in a film. Think about watching a movie. What feels like continuous motion is actually a rapid slideshow of still images flashing by. Neuroscientists believe your perception of time works the same way, with the brain weaving together disjointed sensory inputs into a seamless narrative of now. This 21st model suggests spacetime might not just be out there in the cosmos, it could be partly a fabrication of your mind, shaped by biology as much as physics. Consider how warped time feels during a car crash, those seconds stretching into what feels like minutes, or how a fever can distort your sense of duration. Even mundane moments reveal time's fluidity. Ever noticed how a clock's second hand seems to freeze for an instant when you first glance at it? That's your brain's postdiction at work, retroactively editing sensory data to create coherence. Psychedelics amplify this effect dramatically, with users reporting time loops, eternal moments, or the complete dissolution of past and present. These aren't just hallucinations, they're glimpses of the brain's time construction machinery glitching under pressure. Philosopher Gottfried Leibniz saw this coming centuries ago. While Newton envisioned time as an absolute river flowing uniformly for all, Leibniz argued time and space were relational, meaning they only exist as comparisons between events. A year feels long to a mayfly but short to a galaxy. Modern neuroscience echoes this. Your brain doesn't measure time with a built-in clock, but by tracking relationships between experiences, like the way a melody emerges from notes rather than a metronome. The implications spiral into deep questions. If spacetime is relational, could consciousness itself be part of the equation? Some quantum interpretations suggest observation collapses probabilities into definite outcomes, blurring the line between mind and material reality. Others propose that time's flow is a cognitive illusion, a trick evolved to help organisms sequence actions, meaning the present might be a thin slice of memory and prediction, not an objective feature of the universe. From altered states to ancient philosophy, this model doesn't just challenge how we see clocks, it redefines how we see reality. Whether time is a cosmic given or a neural construct, one thing's clear: your brain isn't just keeping time. It might be writing the score. What if reality isn't something fixed and absolute, but a shimmering dance of perspectives where even the most fundamental properties of particles, or even spacetime itself, only snap into focus when something interacts with them? This is the radical core of relational quantum mechanics, Carlo Rovelli's bold reinterpretation of the quantum world. Forget about electrons having definite positions or spins waiting to be measured. In this 20-second model, properties like position, momentum, or even existence itself are born purely from interactions. Picture two particles colliding. It's only in that fleeting moment of contact that their spin or location becomes real. Before and after, those qualities simply don't exist in any absolute sense. This isn't just philosophy, it's a pragmatic solution to quantum mechanics' notorious measurement problem. Take Schrödinger's cat, the conundrum of whether it's alive or dead before observation. Rovelli's framework sidesteps the paradox entirely by declaring the question meaningless. There's no true state of the cat independent of an interaction. Reality is stitched together moment by moment, like a cosmic game of 20 questions where the answers only materialize when someone asks. The implications for spacetime are staggering. If properties are relational, then distance and duration might not be baked into the universe's fabric. They could emerge from countless tiny exchanges between particles, like a crowd's roar emerging from individual cheers. But this relational web raises profound questions. If reality is observer-dependent, does that mean the moon isn't there when no one looks? Rovelli counters that observer doesn't mean human consciousness. Any physical interaction counts, from a photon striking an atom to two black holes merging. The universe isn't solipsistic. It's a vast network of mutual revelations where every collision, every entanglement, every gravitational tug pulls another thread of reality into view. Yet some physicists balk at relinquishing objectivity. If spacetime is just a tapestry of relations, what anchors it? Where's the loom? These tensions spill into quantum Bayesianism or cubism, our next model, which takes observer dependence even further by weaving in probabilities as personal beliefs. But before we jump there, consider how relational quantum mechanics reframes history itself. Two events might be causally ordered for one observer but simultaneous for another, not because of relativistic time dilation, but because the when is tied to who's asking. It's as if the universe isn't a pre-recorded film but an improv theater troupe, with each participant co-creating the story through their interactions. From spinning electrons to the curvature of spacetime, Rovelli's vision doesn't just tweak quantum theory, it reimagines reality as a living conversation where nothing exists alone and every measurement is a handshake across the void. Quantum Bayesianism, or cubism, turns the traditional view of reality on its head. What if the probabilities in quantum mechanics aren't facts about the world, but personal bets, like a gambler's hunch about where the roulette ball will land? In this 23rd model, the universe isn't a cold, deterministic machine but a collaborative story, where every measurement is an act of meaning-making. Think of it like a cosmic game of charades. The quantum world throws out hints, and it's up to each observer, whether a scientist, a camera, or even a particle detector, to interpret those clues based on their own perspective. When applied to spacetime, this gets even wilder. The distance between stars, the duration of events, even the fabric of reality itself might not be fixed truths but negotiated outcomes, shaped by the very act of observation. Critics argue this veers into solipsism, the idea that only one's mind is sure to exist. If reality is just a collection of personal beliefs, how can we ever agree on objective truths? But cubism sidesteps this neatly by emphasizing that while probabilities are subjective, the tools we use to update them, quantum mechanics math, are universal. It's like two chefs using the same recipe but adjusting the salt to taste. The recipe stays consistent even if the experience varies. This approach dissolves infamous paradoxes like Wigner's friend, where one observer's measurement seems to rewrite reality for another. In cubism, there's no contradiction, just two valid but separate perspectives, like witnesses describing the same event from different angles. Now zoom out to cosmic scales. If spacetime itself is participatory, could the large-scale structure of the universe, galaxies, dark matter, even the cosmic microwave background also depend on interaction? Some cubists speculate that what we call the universe is less a pre-existing object and more a vast, evolving conversation, with each measurement adding another sentence to the story. Imagine a cosmic version of the Mandela effect, where collective observation subtly reshapes reality's contours over time. It's a dizzying thought. The galaxies we see might not just be out there, they might, in some small way, be co-created by the act of looking. Yet cubism isn't without challenges. Traditional realists argue it's a philosophical cop-out. swapping concrete reality for a fog of subjectivity. Others counter that it's the only framework that takes quantum weirdness seriously, embracing the messiness rather than papering it over with hidden variables or parallel worlds. Whether you find it liberating or unsettling, one thing's clear: cubism doesn't just tweak our understanding of space-time. It invites us to see ourselves not as passive witnesses, but as active participants in the universe's unfolding narrative. Stretching across billions of light years like luminous beads on invisible threads, the cosmic web is the largest structure in existence, a sprawling network of galaxies strung along vast filaments, separated by unimaginably empty voids. This isn't random chaos but a fingerprint, an echo of spacetime's earliest moments when quantum ripples in the infant universe were stretched by inflation into the gravitational scaffolding we see today. Picture throwing a handful of sand onto a drum. The grains naturally gather in the valleys between vibrations. Similarly, galaxies didn't form randomly. They coalesced where dark matter's gravitational pull was strongest, tracing out a web-like pattern written into spacetime's fabric from the beginning. The Millennium Simulation, one of cosmology's most ambitious computer models, replayed this cosmic evolution in staggering detail. Starting with a virtual universe just moments after the Big Bang, physicists watched as dark matter's subtle overdensities, those primordial spacetime wrinkles, grew under gravity's pull, drawing ordinary matter into glowing nodes connected by tendrils of gas and stars. The simulation's predictions matched real telescope surveys with uncanny precision, revealing how spacetime's initial texture dictated where galaxies would bloom and where emptiness would reign. Yet mysteries linger, especially in the voids, those yawning gaps between filaments where galaxies are eerily scarce. Some move oddly, as if pushed by unseen forces, leading theorists to speculate these voids might be more than just empty space. Could they be topological defects in spacetime itself, like cracks in frozen ice left over from the universe's phase transitions? The evidence is tantalizing. Certain voids exhibit dark flow, an unexplained drift of galaxy clusters in the same direction, as if something beyond the observable universe is tugging them. Others seem too spherical, their perfect geometry hinting at exotic physics, perhaps relics of cosmic strings, hypothetical spacetime flaws thinner than an atom but stretching across the cosmos, whose gravity could sculpt voids into perfect bubbles. Then there's the integrated Sachs-Wolf effect, where light from the cosmic microwave background subtly shifts as it traverses these empty regions, suggesting voids might be altering spacetime's curvature in ways we don't yet understand. What makes this model so compelling is how it ties the universe's largest scales to its smallest. Those initial quantum fluctuations, magnified by inflation, didn't just shape galaxies. They imprinted a hierarchy of structure that cascades from galaxy clusters down to the distribution of dark matter particles. It's as if spacetime carries a memory of its quantum origins, a fractal echo visible in everything from the cosmic web's grand filaments to the peculiar motions of isolated galaxies. From simulations to sky surveys, each new discovery peels back another layer, revealing how spacetime isn't just a stage for the cosmic drama. It's an active participant, its geometry and defects quietly steering the evolution of everything we see. In 1998, astronomers made a discovery so shocking it overturned centuries of cosmic assumptions. The universe isn't just expanding, it's accelerating, as if some invisible hand is stretching spacetime faster and faster. This phantom force, dubbed dark energy, isn't just mysterious, it's downright bizarre, behaving like anti-gravity, pushing galaxies apart when everything we know says gravity should be pulling them together. Picture blowing up a balloon with dots on its surface. but instead of slowing as it inflates, the balloon starts expanding faster, its dots racing away from each other at ever-increasing speeds. That's our universe, and dark energy is the inexplicable breath filling its lungs. The leading suspect, vacuum energy, a cosmic background hum woven into spacetime itself. Quantum theory predicts that even empty space crackles with fleeting particles popping in and out of existence, and their collective energy could exert negative pressure, literally pushing the universe apart. Einstein actually predicted something similar with his cosmological constant, a term he later called his greatest blunder, but which now looks prescient. The problem: calculations suggest vacuum energy should be a staggering 10 to the power of 120 times stronger than what we observe. It's like expecting a hurricane and feeling only a breeze, a discrepancy so vast it's called the worst prediction in physics history. Enter quintessence, a dynamic alternative. Unlike the static cosmological constant, quintessence imagines dark energy as a field permeating spacetime, its strength ebbing and flowing over cosmic time. Think of it like cosmic weather. Some epochs might see weaker repulsion, others stronger. Some models even allow for phantom energy, where dark energy grows so powerful it could eventually tear atoms apart in a catastrophic big rip. Yet after decades of hunting, no direct evidence for quintessence has emerged, leaving the cosmological constant as the simplest fit to the data, however unsatisfying. Then there's the rebel option. Maybe dark energy doesn't exist at all. Modified gravity theories like tweak Einstein's equations to explain galactic motions without dark matter, and some extensions try to account for cosmic acceleration too. These models suggest spacetime behaves differently on vast scales. Perhaps gravity weakens over enormous distances, mimicking repulsion. But most struggle to explain all observations as cleanly as dark energy, leaving them on the fringe. The stakes couldn't be higher. Dark energy makes up 68% of the universe's energy budget, yet we have no idea what it is. Is it spacetime's intrinsic energy, a field waiting to be discovered, or a sign that relativity needs an overhaul? Upcoming telescopes like Euclid and the Vera Rubin Observatory are mapping billions of galaxies to track expansion's history, hunting for clues in the subtle warping of spacetime. One thing's certain: solving this puzzle won't just reveal dark energy's identity, it could rewrite our understanding of reality's very fabric. The Big Bang wasn't just an explosion, it was the ultimate cosmic paradox. Einstein's equations rewind the universe's expansion to a single point of infinite density, a singularity where spacetime itself frays into mathematical nonsense. Picture squeezing the entire cosmos into a space smaller than an atom, where gravity becomes so intense that the laws of physics as we know them simply stop working. This isn't just a theoretical curiosity, it's a screaming alarm that our understanding of reality is incomplete. But what if the Big Bang wasn't a true singularity at all? What if it was more like a cosmic rebound, the universe hitting a quantum trampoline and bouncing back into existence? Loop quantum cosmology offers exactly that escape hatch. In this model, the universe doesn't collapse into a dimensionless point, but reaches a maximum density where quantum effects take over, turning collapse into expansion. Think of it like compressing a spring, push too far and it snaps back with equal force. Here, gravity itself becomes repulsive at extreme densities, triggering a big bounce from a previous universe's collapse. The smoking gun. Some versions predict subtle imprints in the cosmic microwave background patterns that upcoming telescopes like the Lightbird mission could detect. String theory takes a different route, painting the Big Bang as one event in a vast multiverse. Imagine a cosmic froth where universes constantly bubble into existence, each with its own physical laws. Our universe might be one lucky bubble where the constants allowed galaxies and life to form. This landscape of possibilities could explain why our cosmos seems so finely tuned. If every possible configuration exists somewhere, it's no surprise we find ourselves in a hospitable one. Then there's the wild card, quantum fluctuation. Could the universe have sprung from nothing, a random blip in the quantum vacuum? In quantum field theory, particles pop in and out of existence all the time, so why not an entire cosmos? The math suggests it's possible, though the odds are astronomically low. Unless, of course, inflation, the universe's explosive early growth, was part of the equation. Inflation stretches quantum fluctuations to cosmic scales, potentially seeding not just galaxies but the universe itself. This brings us to inflation's greatest puzzle: what kicked it off? Some theories point to a hypothetical, inflatoned field, a cosmic switch that flipped spacetime into hyperdrive. Others speculate that inflation is eternal, with new universes endlessly budding off like leaves on a tree. Whatever the trigger, one thing's clear: the Big Bang singularity isn't the end of the story, it's the gateway to a deeper mystery, where quantum fuzziness and multiverses rewrite the origin of everything. Imagine a single speck of spacetime, smaller than a proton, suddenly stretching faster than light itself, expanding to cosmic scales in less than a blink. This is inflation, the universe's most explosive growth spurt, and it might not have been a one-time event. According to the inflationary multiverse model, our cosmos could be just one bubble in a frothing sea of universes, each with its own unique physics. Picture a pot of water boiling endlessly. Every popping bubble is a new universe inflating into existence, some with stronger gravity, others with altered particle masses, even some where time flows backward. Our observable universe, with its finely tuned constants, might simply be the lucky bubble where conditions allowed galaxies and us to form. The evidence for inflation hides in the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature fluctuations in this ancient light, patterns no larger than 1 part in 100,000, match predictions of quantum fluctuations stretched to cosmic scales by inflation's relentless pull. It's as if we're seeing the fingerprints of spacetime's quantum origins, frozen in time. But inflation's most startling implication is eternal inflation, the idea that once started, the process never truly stops. Regions of spacetime keep inflating exponentially, birthing new bubble universes in an endless cascade. Some bubbles might collide, leaving scars in each other's cosmic backgrounds. Others could drift forever apart, separated by ever-expanding voids. Yet this raises a profound question: what ignited inflation in the first place? One daring possibility is quantum tunneling from nothing, not empty space, but a state of zero energy and no classical spacetime at all. Think of it like a cosmic Houdini act. The universe escapes the chains of non-existence through a quantum loophole, tunneling into existence as a tiny, unstable patch that then inflates. The math allows it. A fluctuation in the quantum vacuum could nucleate a bubble of spacetime that inflates into a full-fledged cosmos. Critics argue this veers into metaphysics, but proponents counter that the same quantum principles govern everyday phenomena like radioactive decay. If particles can tunnel through energy barriers, why not spacetime itself? The challenge is testing these ideas. Some models predict subtle gravitational waves from inflation's earliest moments, ripples that future observatories might detect. Others suggest rare bubble collisions could leave disk-like imprints in the CMB, like cosmic bruises from a neighboring universe. Whether inflation is a one-time event or a factory for infinite realities, one thing's clear: our universe might be far less unique than we thought. From quantum tremors to colliding bubbles, these ideas stretch the imagination, but they also offer a humbling reminder that the cosmos has never been content to play by the rules we expect. Stephen Hawking once compared the universe to the surface of the Earth, finite but without edges, where asking, "What's before the Big Bang?" becomes as meaningless as asking what's north of the North Pole. This is the essence of the no-boundary proposal, a daring model code developed with physicist James Hartle that reimagines cosmic origins not as a fiery singularity, but as a smooth quantum curve where time itself transforms into something stranger. Imagine the Big Bang not as an explosion from nothing, but as the universe's South Pole, a point where conventional notions of before dissolve into mathematical elegance. The key lies in imaginary time, a conceptual trick where time behaves like a fourth spatial dimension. In this warped geometry, the Big Bang isn't a violent beginning but more like the gradual rounding of a sphere's base. Picture Earth's curvature. There's no sharp edge at the poles, just continuous geometry. Similarly, Hawking and Hartle's universe has no boundary in imaginary time, no moment of infinite density where physics breaks down. Instead, quantum fluctuations gently smooth out the cosmic origin into a fuzzy, probabilistic transition, like watching ice melt in reverse, where jagged edges soften into liquid motion. Critics highlight the proposal's untestability. We can't observe imaginary time or probe beyond the Planck epoch, yet its influence ripples through modern cosmology. The no-boundary idea resonates with quantum gravity theories that treat spacetime as emergent rather than fundamental. Some string theorists see parallels with holographic principles, where the universe's entire history might be encoded on its boundary like a cosmic DVD. Others connect it to loop quantum cosmology's big bounce, where quantum geometry prevents true singularities. What makes this model so compelling is its philosophical audacity. By eliminating the need for a creation event or external cause, it paints a self-contained cosmos, one that could, in principle, explain its own existence through pure geometry. No deities, no multiverses, just a seamless quantum fabric where the universe's birth and its governing laws arise from the same mathematical symmetry. Whether this vision aligns with reality remains unknown, but like a compass pointing beyond known horizons, the no-boundary proposal challenges us to rethink not just how the universe began, but what beginning even means. What if the universe isn't the ultimate reality, but an advanced civilization's version of a hyper-realistic video game, with spacetime itself rendered on a cosmic quantum computer? This is the spine-tingling premise of the simulation hypothesis, where the smooth curves of relativity and the fuzzy probabilities of quantum mechanics aren't fundamental truths, but artifacts of a computational engine humming beneath reality's surface. Picture spacetime as a vast grid of pixels, each a Planck length in size, the smallest possible resolution of the simulation. Just as your computer screen can't display an image finer than its pixels, the universe might hit a computational limit at these scales, revealing its digital skeleton in subtle ways. The most compelling case for this model comes from philosopher Nick Bostrom's trilemma, which lays out three stark possibilities. Either almost all civilizations self-destruct before reaching post-human technology, or none choose to run ancestor simulations, or we're almost certainly living in one. The logic is chillingly simple. If future civilizations develop the power to simulate conscious minds, they'd likely create countless virtual worlds outnumbering base reality by astronomical margins. Statistically, the odds tilt heavily toward us being in a simulation. Elon Musk famously quipped that the chance we're in base reality is 1 in billions. But how would we know? Proponents suggest hunting for glitches, tiny imperfections in the fabric of spacetime that might emerge when the simulation's processors are overloaded. High-energy particle collisions, like those in the Large Hadron Collider, could be prime hunting grounds. If spacetime is pixelated, smashing particles together at near-light speeds might reveal unexpected energy cutoffs or anomalies in scattering patterns, like a video game struggling to render explosions at maximum zoom. Some physicists even propose that the very weirdness of quantum mechanics, with its probabilities and observer effects, could be a sign of optimization shortcuts in the cosmic code. Yet the simulation argument isn't without pushback. Critics argue it's unfalsifiable, a modern-day version of Descartes' evil demon, impossible to disprove but offering no testable predictions. Others point out the staggering energy requirements. Simulating every quark in every atom would demand more computational power than the universe itself contains. Unless, of course, the simulators use clever compression, rendering only what's observed, a cosmic version of video game level of detail optimizations. What makes this model so provocative isn't just its sci-fi appeal, but how it reframes spacetime's nature. If reality is computed, then dimensions, forces, and even time itself might be emergent properties of deeper algorithms. From Planck-scale pixels to quantum indeterminacy, every mystery of modern physics could be a clue, not to how the universe works, but how it's coded. Whether you find the idea exhilarating or unsettling, one thing's clear: the simulation hypothesis doesn't just challenge our place in reality, it redefines what reality might actually be. Quantum mechanics has always played by strange rules, but none are more mind-bending than the observer effect, the idea that simply measuring a particle can fundamentally alter its state. Now stretch that principle to cosmic scales, and you arrive at an electrifying possibility. What if the universe itself only took shape because something observed it? This isn't mysticism, it's the daring intersection of quantum theory and cosmology, where consciousness isn't just a byproduct of reality, but might be woven into its very foundations. John Wheeler, the physicist who coined the term black hole, took this idea furthest with his participatory universe hypothesis. Picture the Big Bang not as a definitive starting gun, but as a quantum haze of possibilities, a superposition of every potential universe. Only when an observer, whether human or otherwise, interacted with this primordial quantum soup did the wave function collapse into the concrete reality we know. Wheeler's delayed choice experiment illustrates this beautifully. Photons behave as particles or waves depending on how we choose to measure them. Even if that choice happens after the photon's decision should have been made. Now extrapolate that to the cosmic microwave background, the universe's oldest light. Could its patterns reflect not just random quantum fluctuations, but the imprint of some primordial act of observation? Von Neumann took this further, suggesting consciousness itself might be the ultimate measuring device that resolves quantum uncertainties. In his quantum mind theory, subjective experience isn't separate from physics. It's the mechanism that crystallizes probability into fact. This leads to startling implications. If observation creates reality, then the universe might be a self-exciting loop, where consciousness emerges from quantum processes, and those very processes depend on consciousness to manifest. It's like a cosmic Ouroboros the snake eating its own tail. Critics argue this veers dangerously close to solipsism, reducing the universe to a projection of mind. But proponents counter with a subtle distinction. They're not claiming humans dreamt the cosmos into being, but that observation in the broadest sense, any interaction that exchanges information, might be the engine of reality. Even a single photon striking a dust particle could count as an observation capable of collapsing quantum possibilities. The echoes of this idea ripple through modern physics. In quantum Darwinism, only states robust enough to be observed by multiple systems survive decoherence, suggesting reality isn't just built by observation, it's honed by consensus. Meanwhile, the holographic principle hints that information about the entire universe might be encoded on its boundary, like a cosmic movie screen where observation plays the projection we experience as spacetime. Whether consciousness is a cosmic architect or just a curious bystander, one thing's clear: the boundary between observer and observed has never been so thrillingly blurred. From Wheeler's quantum riddles to von Neumann's metaphysical leaps, these models don't just challenge what reality is, they redefine who or what gets to decide. Time crystals sound like something straight out of science fiction structures that move without energy, ticking like perpetual cosmic clocks even in their lowest energy state. Predicted in 2012 by Nobel laureate Frank Wilczek, these bizarre quantum objects defy one of nature's most fundamental assumptions: time symmetry. Normally, physical systems in their ground state, their most stable, lowest energy configuration should look identical at every moment in time. But time crystals break this rule, oscillating in a repeating pattern without any external push, as if the universe itself handed them an eternal wind-up key. The first experimental proof came in 2017 when researchers used chains of trapped ytterbium ions, laser-cooled to near absolute zero, to create this exotic phase of matter. The ions flipped their spins in a regular rhythm, not because they were driven by energy, but because their quantum interactions locked them into an unending dance. It's like a pendulum that swings forever without gravity or friction, its motion encoded in the very fabric of its quantum structure. This discovery didn't just add a new state of matter to textbooks, it hinted that time itself might have hidden layers of symmetry we've yet to fully grasp. What makes time crystals truly mind-bending is their potential to reshape our understanding of spacetime. If matter can exhibit periodic motion without energy input, could there be structures in the universe, natural or artificial, that exploit this loophole to create stable time loops? Some theorists speculate that time crystals might be the first step toward engineering closed time-like curves, hypothetical paths through spacetime that loop back on themselves. Imagine a cosmic Möbius strip where cause and effect bend into a circle, allowing information or even particles to revisit their own past, yet the paradoxes loom large. Time crystals don't violate thermodynamics, they don't create energy from nothing, but their existence challenges our notions of equilibrium and spontaneity. If time's arrow isn't as rigid as we thought, could other symmetries break in ways we've yet to imagine? From quantum computers exploiting time crystals for error-resistant memory to the wild possibility of spacetime itself having crystalline properties on cosmic scales, this discovery blurs the line between science and speculation. Whether they're a curiosity or a key to deeper physics, one thing's certain: time crystals don't just tick, they rewrite the rules of the clock. Time travel isn't just a sci-fi trope, it's a mathematical certainty lurking in Einstein's equations, waiting to be unraveled. In 1949, Kurt Gödel shocked the physics world by discovering a solution to general relativity that allowed for closed time-like curves, paths through spacetime that loop back on themselves, letting you return to your own past without breaking any physical laws. Picture walking in a straight line around the Earth only to end up where you started, but instead of space, it's time itself that bends into a circle. Gödel's universe wasn't just a thought experiment. It was a rotating cosmos where the very fabric of reality twisted into cosmic Möbius strips, offering a one-way ticket to yesterday. But here's the catch: closed time-like curves breed paradoxes like the infamous grandfather paradox. What if you travel back and accidentally prevent your own birth? Quantum mechanics offers two escape routes. The first is the Novikov self-consistency principle, which insists the universe enforces logical harmony. Any attempt to alter the past would inevitably conspire to preserve it, like a cosmic game of Tetris where every move inevitably fills the gaps. Imagine firing a bullet at your grandfather only for the gun to jam or your aim to falter, not by chance but by necessity. The second, even wilder, solution comes from parallel timelines where branching realities absorb contradictions. In this view, changing the past doesn't rewrite history, it spawns a new one, like a river forking around a rock. Yet nature seems to abhor time loops. The weak energy condition, a bedrock principle of physics, suggests closed time-like curves require exotic matter with negative energy, something we've never observed. Even wormholes, the darlings of time travel lore, would need this phantom material to stay open, but impossibility hasn't stopped physicists from probing these ideas. In 2020, researchers simulated a quantum system where information cycled back in time, observing how quantum entanglement could, in theory, stitch causality back together. What makes closed time-like curves more than just mathematical curiosities is how they stress-test relativity. They reveal spacetime's plasticity, its capacity for geometries so warped they defy intuition. From Gödel's spinning cosmos to quantum self-correction, these models don't just ask whether time travel is possible, they force us to confront what time even is when the universe holds a mirror to its own past. Imagine folding the vast emptiness between stars like a piece of paper, bringing distant worlds within reach without breaking the cosmic speed limit. This is the promise of the Alcubierre warp drive, a theoretical engine that doesn't push a ship through space, but instead manipulates spacetime itself, creating a wave that carries the vessel faster than light without ever locally exceeding light speed. Picture a surfer riding a wave. The water itself moves little, but the surfer glides effortlessly forward. In this model, spacetime becomes the wave, compressed tightly in front of the ship and expanded behind it, forming a warp bubble that sidesteps relativity's strict speed limits. The math behind this idea traces back to Miguel Alcubierre's ground-breaking 1994 paper, which showed that Einstein's equations allow such distortions if you have the right fuel, specifically exotic matter with negative energy density. This bizarre substance, predicted in quantum field theory as Casimir vacuum fluctuations, would act like anti-gravity, repelling spacetime rather than attracting it. The catch: early calculations suggested the energy requirements were absurd, equivalent to converting Jupiter's entire mass into pure energy, but recent breakthroughs hint at workarounds. Quantum physicists discovered that altering the warp bubble's shape, making it thinner or oscillating, could slash energy needs by orders of magnitude, perhaps even to the mass of a small spacecraft. NASA Eagleworks Lab, a skunkworks operation dedicated to far-out propulsion ideas, has dabbled in tabletop experiments to test these principles. Using laser interferometers, they've attempted to detect microscopic spacetime distortions akin to a warp bubble's precursor. While no breakthrough has been confirmed, the mere existence of such experiments signals a seismic shift. Faster than light travel, once the realm of fiction, is now a credentialed field of study. Yet, even if the energy puzzle is solved, new challenges emerge. A warp bubble's leading edge would concentrate enough energy to vaporize anything it touches, making interstellar navigation a cosmic minefield. There's also the unsettling possibility that the bubble's interior would become causally disconnected from the universe, trapping passengers in a pocket of spacetime with no way to steer or stop. Some theorists even speculate that creating a warp bubble might inadvertently spawn a black hole or tear spacetime itself, but the dream persists, fueled by tantalizing possibilities. Recent simulations suggest warp drives might leave detectable gravitational waves signatures we could search for with next-gen observatories. Others propose that advanced civilizations, if they exist, might already be warping spacetime in ways we could spot through anomalous starlight distortions. Whether humanity ever builds a warp drive remains uncertain, but the mere fact that physics allows the possibility rewrites our vision of the cosmos not as an impassable gulf, but as a dynamic fabric waiting to be shaped. Black holes aren't just cosmic vacuum cleaners, they're existential riddles wrapped in event horizons, and their greatest paradox threatens to unravel the foundations of physics itself. At the heart of the crisis lies a brutal contradiction. Quantum mechanics insists information can never be destroyed, while black holes appear to shred it into oblivion. Picture tossing a book into a fire. The pages burn, but in principle, every word could be reconstructed from the smoke and ash. That's quantum unitarity in action. Now throw that book into a black hole, and according to classical physics, it's gone forever. It's information locked behind a one-way gravitational vault. The problem, quantum law says that's impossible. Stephen Hawking's eureka, a moment came when he realized black holes aren't completely black. They emit radiation, slowly evaporating over eons. This Hawking radiation seemed like a potential escape hatch. Perhaps information leaks out, encoded in the radiation's subtle fluctuations. But here's the twist. Hawking's calculations suggested the radiation is purely thermal, carrying no more information than the glow of a light bulb. It's like expecting a shredded document to reassemble itself from confetti, except the confetti is random noise. For decades, this information paradox divided physicists into warring camps. Some, like Leonard Susskind, championed the holographic principle, arguing that data isn't lost but smeared across the event horizon like a cosmic scratchpad. Others, like Hawking himself, initially bet information was truly erased, a stance he later recanted in a famous concession written in fire. Then came the Firewall controversy. In 2012, a bombshell paper argued that preserving information at the event horizon would require a blazing wall of high-energy particles, a death zone that would incinerate anyone crossing it. This violated Einstein's vision of smooth spacetime, where falling into a black hole would feel uneventful until tidal forces took over. The firewall wasn't just a threat to astronauts, it was a crack in the bedrock of general relativity. The stakes couldn't be higher. If information truly vanishes in black holes, quantum mechanics, the most accurate theory in history, needs rewriting. If it escapes via Hawking radiation, we might need a theory of how spacetime itself encodes data. And if firewalls are real, Einstein's smooth geometry crumbles at the horizon. Recent breakthroughs in quantum error correction offer a tantalizing middle path. Information might not be lost or carried away, but intricately entangled in the black hole's quantum structure, like a message hidden in the knots of a tangled rope. The holographic principle takes this further, suggesting the real action happens on the black hole's surface, with the interior acting as a cosmic projection. What makes this paradox so pivotal is how it forces us to choose between cherished theories, or invent a new one that transcends both. From Hawking's radiation to holographic whispers, each solution peels back another layer of spacetime's deepest mystery. Is the universe fundamentally a place where information lives forever, or are black holes the ultimate shredders of reality? The answer might not just resolve a paradox, it could reveal whether spacetime is a stage or a story written in quantum code. Deep in the labyrinth of quantum physics lies a geometric shape so revolutionary it renders spacetime obsolete, the amplituhedron. Picture a jewel with countless facets, each encoding the probabilities of particle interactions without any reference to space, time, or even causality. This isn't science fiction, it's a discovery that rewrites the rulebook of reality itself. Traditional calculations for particle collisions, like those at the Large Hadron Collider, involve agonizingly complex equations spanning thousands of terms, tracking every possible path particles might take. But the amplituhedron sidesteps this chaos entirely, collapsing those calculations into a single, elegant geometric volume. It's like trading a tangled ball of yarn for a perfectly folded origami swan. Same essence, radically simpler form. The magic lies in its defiance of locality, the idea that particles must interact through points in spacetime. Instead, the amplituhedron treats particle interactions as abstract relationships, where outcomes depend solely on the shape's volume and boundaries. Imagine two dancers performing a duet without a stage, their movements defined not by positions but by pure geometry. This aligns eerily with quantum entanglement, where particles coordinate instantly across vast distances, as if spacetime were a mere afterthought. Could the amplituhedron be revealing a deeper layer of reality, where the universe's true language isn't forces or dimensions, but mathematics itself? Yet the amplituhedron's implications stretch beyond simplification. If particle physics can be perfectly described without spacetime, what does that say about spacetime's fundamental nature? Some theorists speculate spacetime might emerge from these geometric structures like a hologram projected from a hidden code. Think of it like watching a 3D movie. The depth feels real, but it's just light playing tricks on a flat screen. Similarly, the amplituhedron hints that our experience of space and time could be a shadow cast by a more primal, mathematical reality. Of course, this model is still in its infancy. The amplituhedron currently applies only to specific quantum field theories, like the ultra-simplified, planar version of particle interactions. Scaling it up to encompass all physics, gravity included, remains a towering challenge. But the tantalizing possibility remains. If spacetime isn't the foundation of reality but a derivative illusion, we might be standing at the brink of a Copernican-level revolution. From collider data to cosmic mysteries, the amplituhedron doesn't just solve equations, it invites us to question whether the stage of the universe exists at all. Gravity has always been the universe's most familiar mystery, the force that sculpts galaxies and pins us to the ground, yet resists every attempt to reconcile it with quantum mechanics. But what if we've been thinking about it all wrong? Enter Eric Verland's explosive theory of emergent gravity, where the pull we call gravity isn't a fundamental force at all, but a side effect, a cosmic illusion born from the way information organizes itself at the quantum level. Picture an ice skater gliding effortlessly across a rink. The smooth motion feels like magic, but it's really just the collective behavior of countless molecules aligning beneath the blades. Verland suggests gravity works the same way, not as a force transmitted through spacetime, but as a statistical tendency, a kind of quantum peer pressure that emerges when entropy, the universe's drive toward disorder, reshapes the fabric of reality itself. The theory's brilliance lies in its elegant solution to one of astronomy's biggest headaches, dark matter. For decades, we've clung to the idea that invisible particles must explain why galaxies rotate faster than their visible mass suggests. But Verland's math offers a radical alternative. Imagine a crowded room where people cluster together. The density of bodies creates emergent forces, like the push and pull of a dance floor. Similarly, emergent gravity proposes that the extra tug holding galaxies together isn't unseen matter, but a natural consequence of how quantum information redistributes in deep space. The controversial part, it ditches dark matter entirely, rewriting galactic dynamics as a thermodynamic effect. Early studies found eerie alignments between Verland's predictions and galaxy rotation curves. no dark matter required. Yet the physics community remains deeply divided. Critics argue that emergent gravity struggles to explain phenomena like the bullet cluster, where colliding galaxies seem to separate visible matter from its gravitational effects, a smoking gun for dark matter's existence. Others point to mathematical gaps, like the theory's current inability to fully account for Einstein's precise predictions in our solar system. Verland counters that emergent gravity isn't just a tweak to relativity, it's a paradigm shift, one that might require redefining inertia, acceleration, and even the nature of spacetime itself. The stakes couldn't be higher. If Verland is right, gravity joins temperature and pressure as an emergent property, a collective behavior with no more fundamental status than the wetness of water. It would mean the universe runs not on forces but on information, with spacetime itself as a kind of holographic dashboard displaying the deeper quantum reality. From black hole thermodynamics to quantum entanglement, emergent gravity doesn't just challenge our textbooks, it dares us to see the cosmos not as a machine of particles and forces, but as a dynamic network of relationships where every tug and orbit whispers the hidden language of entropy. Spacetime as we know it, the smooth, four-dimensional fabric of relativity, might not be the bedrock of reality, but a fleeting illusion, a phase transition in a far stranger cosmic order. Imagine waking up one day to discover the ground beneath your feet isn't solid earth, but a thin crust of ice floating on an ocean of something deeper. That's the radical proposition of this 37th model. Spacetime itself could be a temporary structure, a holographic projection woven from quantum entanglement and error-correcting codes, destined to dissolve into a more fundamental layer of reality we've yet to comprehend. At the heart of this idea lies a startling convergence of theories. The holographic principle suggests our three-dimensional universe might be encoded on a two-dimensional surface, like a movie projected from the edge of existence. Quantum entanglement stitches these projections together, creating the illusion of distance and continuity. What we perceive as spacetime might just be the collective behavior of trillions of entangled quantum bits, humming in unison. And then there's matrix theory, a bold extension of string theory that reimagines reality as a dynamic network of zero-dimensional objects, points interacting in ways that give rise to space, time, and even gravity as emergent phenomena. Picture the pixels on your screen. Individually, they're just dots of light, but together they create the seamless motion of a film, the most mind-bending implication. Spacetime's fragility. Just as ice melts into water under heat, the smooth geometry of relativity might melt into a froth of quantum information at extreme energies or in the distant future. Quantum error correction, a concept borrowed from computer science, hints at how this could work. In quantum computers, error-correcting codes protect fragile qubits from decoherence by spreading their information across many particles. Some theorists, like Brian Swingle and Leonard Susskind, argue spacetime itself might function similarly, with the fabric of reality acting as a cosmic error-correcting code that maintains coherence across vast distances. A crack in this code, a severe enough disruption, could unravel spacetime entirely, revealing the raw quantum data beneath. What would this deeper layer look like? In matrix theory's framework, the building blocks aren't particles or strings, but abstract mathematical relationships, a cosmic spreadsheet where every cell's value depends on every other. Time and space wouldn't be fundamental. They'd emerge from the matrix's evolving patterns, like the plot of a novel emerging from the arrangement of words on a page. This isn't just philosophy. Experiments with quantum simulators, ultra-cold atoms manipulated to mimic exotic physics, have already recreated holographic-like behaviors in labs. where lower dimensional systems spontaneously generate higher dimensional geometries. The implications rewrite our cosmic story. If spacetime is a phase, then the Big Bang might not have been the origin of reality, but the moment this phase began, like water freezing into ice. And its end, a big melt, where the universe's quantum code finally overloads, dissolving the stage and leaving only the actors, pure information, dancing in the dark. From holograms to matrices, these models don't just challenge our place in the universe, they suggest the universe itself might be a temporary glitch in something far grander, a fleeting pattern in an infinite cosmic computation. The future of spacetime isn't just a theoretical puzzle, it's a frontier being cracked open by revolutionary tools, from quantum computers humming in labs to telescopes piercing the veil of Planck-scale physics. Imagine a quantum processor like Google's Sycamore or IBM's Condor simulating spacetime's granular structure, not with equations on a chalkboard, but by orchestrating qubits to mimic how spacetime itself might behave at scales a billion times smaller than an atom. These machines don't just calculate, they emulate, offering a sandbox to test whether spacetime emerges from quantum entanglement or dissolves into a froth of loops and strings. Already, experiments with superconducting circuits have recreated toy versions of black holes, observing how information might escape their grasp, a glimpse into physics that no telescope could yet capture. Meanwhile, the James Webb Space Telescope peers back to the universe's infancy, hunting for anomalies in the cosmic microwave background, subtle fingerprints of quantum gravity or extra dimensions. Its infrared eyes might spot primordial black holes, relics of the Big Bang that could validate string theory's predictions. On Earth, LIGO gravitational wave detectors listen for spacetime ripples from colliding neutron stars, their echoes potentially carrying hints of exotic physics, like violations of Lorentz symmetry, which would signal that spacetime isn't as smooth as Einstein imagined. And deep under the Alps, CERN Future Circular Collider could smash particles with such force that it momentarily recreates conditions last seen a trillionth of a second after the Big Bang, probing whether spacetime melts into a quark-gluon plasma or reveals hidden symmetries. But the real breakthroughs may come from unexpected collaborations. Picture a gravitational wave observatory on the Moon, free from Earth seismic noise, or a network of atomic clocks in space so precise they detect spacetime wobbles caused by passing dark matter. Theorists and experimentalists are now speaking the same language, with AI sifting through data for patterns no human could spot, like neural networks trained to find traces of wormholes in galactic rotation curves. The next decade won't just refine our models, it could force a paradigm shift. If quantum computers simulate a universe without spacetime, if telescopes catch light bending in ways relativity can't explain, or if colliders uncover particles from extra dimensions, physics may face its greatest upheaval since quantum mechanics. From holographic codes to emergent dimensions, the future of spacetime isn't written in the stars, it's being coded in labs, etched in data, and whispered in the echoes of cosmic collisions. The only certainty, the universe's greatest mysteries won't stay hidden for long. We've journeyed through 38 revolutionary models, each peeling back another layer of spacetime's mysteries, from Einstein's elegant curvature to the holographic hum of quantum information. Some theories paint spacetime as a cosmic trampoline, bending under the weight of stars, while others dissolve it entirely into a shimmering illusion, woven from entanglement and error-correcting codes. Whether you're captivated by the block universe's frozen eternities, the chaotic dance of quantum foam, or the audacious possibility that reality itself might be a simulation, one thing's undeniable: the universe refuses to play by the rules we've written for it. Think about the implications. If spacetime emerges from something deeper, quantum loops, holograms, or even computational bits, then everything from black holes to the passage of time might just be surface-level phenomena, like waves on an ocean we've only begun to fathom. And if models like Verlin's emergent gravity or the amplituhedron hold water, we might be on the brink of a Copernican-level upheaval where gravity isn't a force and particles don't move through space, they define it. The beauty of these ideas isn't just in their strangeness, but in how they invite us to participate. Science isn't a monologue. It's a conversation spanning generations where each theory, no matter how outlandish, adds another voice to the chorus. So tell us, which model left you awestruck? Do you see spacetime as a cosmic stage, a quantum network, or something even wilder? Drop your thoughts below and let's keep the discussion soaring. If this cosmic roller coaster left you hungry for more, hit that subscribe button. We've got universes of mysteries left to explore. From warp drives to white holes, the next adventure is just a click away. Until then, stay curious, stay bold, and remember, the universe's greatest secrets aren't hidden in the stars. They're waiting just beyond the edge of what we think we